Chapter 21, Quiz 2, which is the same as Chapter 21, Homework Problem number 8. In this problem, you're working with three conductors, sphere A, B, and C. A conductor is a material that allows charges to pass through it. An insulator doesn't allow charges to flow, and a semiconductor sometimes allows charge flow. Those are the three basic categories: conductor, insulator, and semiconductor. This problem describes two experiments. There's a sequence of events for experiment number 1 and a sequence of events for experiment number 2. To me, when I read through this problem, my first thought is to create a table. It's pretty confusing and there's a lot going on. So my instinct is to tabulate everything or create a series of diagrams. Ultimately, after going through experiment 1 and experiment 2, you need to find the ratio of the electrostatic force between A and B at the end of experiment number 2 with respect to at the end of experiment number 1. This sounds very complicated to me. My instinct, again, is to create a table and maybe to create a series of visuals that support what's going on as a first step. Okay, so I'm going to read through this problem a whole bunch of times and cough up multiple drafts of a table until I get something that makes sense to me. This is a pretty time-consuming process, but it's worth it. Plus, once you do stuff like this enough times, you get pretty efficient. So after several draft versions and a pretty decent amount of time, here's what I finally came up with. To me, this process was very helpful to get my head wrapped around what was going on. The overarching lesson of this problem is conservation of charge. Spheres A, B, and C start off with a charge of 4Q, -7Q, and 0 respectively. This unit, capital Q, represents a charge unit. There are two common units of charge, the coulomb and the fundamental charge. For now though, we can be happy with Q, some amount of charge. Let's go through this in detail. Experiment 1, step 1. Sphere C, which has an initial charge of 0Q, is brought into contact with sphere A, which has an initial charge of 4Q. Because all spheres here are conductors, charges can move freely through them and between them. Sphere C looks really attractive to sphere A. Sphere A is occupied by positive charges. Opposites attract and legs repel. All of this mutual repulsion on sphere A means some of the charge on sphere A will conduct and move over to sphere C. Here's the final result. Sphere C has a charge of 2Q and sphere A has a charge of 2Q. Notice that charge is conserved. I end up with a grand total of positive 4Q worth of charge. 2 plus 2 equals 4. And I started off with a positive 4Q amount of charge. 0Q plus 4Q also equals 4Q. Let's continue with step 2. Sphere C is now brought into contact with sphere B. All of that positive charge on sphere C is mutually repulsive. All of that negative charge on sphere B is also mutually repulsive. Notice that before sphere C is brought into contact with sphere B, collectively they represent a grand total of -5Q amount of charge. After sphere C contacts sphere B, this distributes evenly. Sphere C ends up with -2.5Q and sphere B also ends up with -2.5Q. Charge is once again conserved. I started off with a grand total amount of -5Q because positive 2Q plus a -7Q equals a -5Q, and that's what I ended up with after the contact. So here's my final result for experiment number 1. Sphere A now has a charge of 2Q, B -2.5Q, and sphere C has a charge of -2.5Q. Let's run experiment number 2. All of the spheres return to their initial states of charge. Sphere C contacts sphere B. Here's the result. Sphere C ends up with a charge of -3.5Q, and sphere B ends up with a charge of -3.5Q. Before contact, there was a -7Q amount of charge, and after contact, there's still -7Q worth of charge. Charge is conserved, but charges can flow and redistribute. Step 2, sphere C, which now has a charge of -3.5Q, contacts sphere A, which is at its initial state of positive 4Q. Before contact occurs, I have -3.5Q plus 4Q, or 0.5Q before contact. After contact, C has a charge of 0.25Q Q, and A has a charge of 0.25 Q. So the charges have redistributed, but charge is conserved, and I end up again with 0.5 Q amount of charge. Here's my final result. Sphere A ends up with a charge of 0.25 Q, B ends up with negative 3.5 Q, and sphere C ends up with a charge of negative 3.5 Q. Okay, now we're ready to finally answer the question. What is the ratio of the electrostatic force between A and B at the end of experiment 2 to that at the end of experiment number 1? The electrostatic force between A and B is given by Coulomb's law. Here's Coulomb's law. Specifically, here's Coulomb's law for the electrostatic force between A and B at the end of experiment number 2 in the numerator, and here's Coulomb's law for the electrostatic force between A and B at the end of experiment number 1 in the denominator. This is the ratio I need to find. Take this ratio and cancel everything that can be canceled and simplify, and you'll get the right answer.